Hello everybody! In the previous videos through science lenses, we started our discussion about science and scientific way of thinking. We briefly checked presuppositions, terms, criteria, features which science is based on, and looked over few risks and limits in connection with science. Let's continue our discussion with two videos, Methods of Science. It's very important to know and use certain effective and proven methods, models and instruments to achieve results. Science also uses several of them. Ready to learn or maybe remind them? The first couple methods are deduction and induction, or inductive and deductive logic. What is logic? Let's have two examples of reasoning to make a conclusion. Only one example out of two will be with good reasoning, leading to the right outcome. Guess which one? The first example. It's very bright in the room, therefore it's a daytime now. The second one. I can see sun high in the sky, therefore it's a daytime now. Logic is the separate science branch of correct reasoning which helps to distinguish good reasoning from bad. Logic sorts out the relationships that are fundamental in science, the relationship between hypothesis and evidence, between premises and conclusions. The most immediate benefit derived from the study of logic is the skill needed to construct own arguments and to evaluate the arguments of others. It's very important to study best practices and ways of good reasoning. It could help in virtually any aspect of your life. Isn't it motivating? Now let's see the difference between deductive and inductive logic. Deductive reasoning is a model of human reasoning which allows to make conclusions based on initial given premises. Let's have an example with three statements. Premise number 1. Every mammal has a heart. Premise number 2. Every dog is a mammal. Conclusion. Every dog has a heart. Argument, by one of the definitions, is a series of statements used to present reasons for accepting conclusions. Deductive argument is an argument which contains initial given premises and conclusion, implicitly, explicitly connected by rules of logic. Deductive argument can be valid as well as can be invalid. A deductible argument is valid if the truth of its premises guarantees the truth of its conclusions. So, recent example about dogs' hearts, which contains two premises and conclusion, together with certain not explicitly mentioned rule of logic, is an example of deductive argument. And this argument is actually a valid one. There is a list of different deductive argument types with their rules, which can be found in books or online. If you know the structure of certain deductive argument and understand rules of its logic underneath, you can use them to confirm truth of a conclusion. Let me mention again how you can confirm it. If all premises are truthful, the conclusion of a valid deductive argument is true with 100% certainty. The main limitation is that deductive reasoning doesn't allow you to learn anything new at all, because all logical argument depends on assumptions and given mental model. Model could be wide enough, but deduction anyway narrows this given model down to a specific particular expected data. As a result, narrowing cannot help to learn new, but it can allow to achieve a result of deduction, in particular to conclude or to find expected data. Like, for example, making explicit outcome that dogs should have hearts. Initial given model has more room to potentially place hearts inside other mammals, which were not discussed within argument explicitly. That was about deductive logic as scientific method. Let's move further. Inductive reasoning pursue answers to different kinds of questions, if compared with deductive reasoning. The direction of inductive reasoning is from actual data to a mental model. In other words, inductive reasoning is an activity of the mind that takes us from the observed to the unobserved, as per David Hume, lived in 18th century. Please look to an inductive argument consisting of just one premise and conclusion. Premise number 1. Every dog that has ever been observed has had a heart. Conclusion. every dog has a heart. If you remember previous example about deduction with two premises and conclusion, the conclusion of a deductive argument is already contained, usually implicitly, in its premises, whereas the conclusion of recent inductive argument goes beyond the information present. Conclusion hasn't been observed yet. We have prediction, kind of future telling in conclusion. According to one common view of science, scientists spend much of their time trying to induce general laws about categories from particular examples. Do you remember Nicolaus Copernicus, whom we discussed in the very previous video through science lenses? He was able to bring new heliocentric model with Sun in the center of our solar system. He didn't knew about it. And history tells us that no other human knew at his time. So he worked with some mathematical data and observations, and based on inductive logic came with a brave conclusion for his 16th century time. Scientific world before Copernicus was sure that geocentric model is the right one, where all planets and sun travel around the Earth. I guess it was probably very hard for Copernicus to overcome confirmation bias, human logical mistakes discussed in the previous video as well, and assume that all other people were wrong with geocentric model exist at that time. Very good example of overcoming biases, which should be the case for all scientists whenever possible. And if you could think for a while, it's also a bright example of using inductive logic. By the way, remember, deductive argument can be valid or invalid, as we discussed earlier. An inductive argument, however, can be strong or weak. An inductive argument is strong if its premises support the truth of its conclusions to a considerable degree. Interesting thing to compare. Given the truth of all its premises, the conclusion of valid deductive argument is true with 100% certainty. But for inductive argument, it's different. Even given the truth of all its premises, the conclusion of an inductive argument is true with at most high probability, but not absolute certainty. The greatest certainty of deduction is because conclusion says nothing that was not already stated by the premises. On the other hand, because inductive conclusion says something not given in the premise, that the conclusion might be false even though the premise is true. Let me bring doubt to our inductive argument mentioned earlier with conclusion that every dog has a heart. What if some dog has had a mechanical pump for veterinary research instead of heart? As you can see, we may miss something in conclusion which was not yet observed by us. In the contrary, to support deduction, certainty, deductive reasoning task has two key instructions. First one. People must be told to assume the premises are true and usually are told to base their reasoning only on these premises, which is our strict given mental model. For example, we are certain by premises that all mammals have hearts, and we are certain about dogs being mammals. We were explicitly not given any premise about any exceptions to assume other variants. Nothing is stated, for instance, that some dogs can have replaced hearts with mechanical pumps. Important thing, we need to agree that strength of the logical deduction is completely dependent on the accuracy of the premises. Second key instruction for deductive reasoning. People must only draw or endorse a conclusion that necessarily follows from the premises. For our example, we are not making outcome about cats or about reptiles, but exactly about dogs and mammals, as only stated in premises. As you can see, there is less or even no room for uncertainty within deductive reasoning, if compared with inductive one. We have just finished discussion about deductive and inductive logic, which are heavily used in science. Please remember, typically deduction reasons from general to specific, whereas induction reasons in the opposite direction, from specific cases to general conclusions. Couple of methods used by science are probability and statistics. On the level of common sense, probability means a chance or likelihood. Probability is a natural tendency for an event to occur or to become real, if we talk about events. If we talk about statement or proposition, Probability is the natural tendency for statement to be true. Most events with low probabilities are not or will not become real, whereas most with high probabilities are or will become real. Same for statements, propositions in regards of becoming true. So when you see weather forecast with 90% chance of rain, you can make a conclusion that it's a very high probability for rain to occur. But still there is a low chance for rain not to happen, because they don't give you 100% probability, but just 90%. Probability is important because in many cases the best answers that science can deliver are more or less probable conclusions, rather than absolute certainties. So when constructing deductive argument, for example, probability can play significant role. We cannot be sure all the time about only specific conclusion. In real life, it may not be completely black, it may not be completely white, but somehow gray to a certain degree. For example, if you add third premise into our deductive argument discussed earlier that veterinary clinic in your city can replace dog's heart with a mechanical pump, there is a chance to have dog with mechanical pump instead of a heart. As a result, certainty in our conclusion disappears. There will be no certainty in our prior conclusion. In other words, we would have less than 100% probability for all dogs in our city to have hearts. Probability can vary from high numbers, close to 100%, to low numbers, close to 0%. Probability can be embedded in a premise of deductive argument, not only in conclusion. For example, we may have calculation tasks with flipping a coin, and given model may have flipping fair coin included in one of its premises. Please note that fair coin by definition is a coin which gives heads with 50% probability and tails with the same 50% probability. There might be unfair coins, for example, if you want to cheat someone as a casino owner and make one side of the coin heavier to give higher probability either for heads or tails. We don't plan to go deeper with the topic about probability. It's a huge one, starting from objective or physical probability versus subjective or personal probability, and finishing with difficult equations and theorems. You're welcome to read yourself when needed. That was briefly about probability in science. Another scientific tool to briefly discuss is statistics. Statistics is a set of methods used to collect and analyze data. And sometimes they name statistics as applied inductive logic. How statistics can be helpful in science? When we come from observed to unobserved using induction, we need to collect enough supportive evidence with specific certainty prior, which is exactly subject of statistics. So if, for example, you know that iron melts at 1535 Celsius based on few actual observations, and you probably want to know what should be proper range of temperatures of iron melting point from different regions and therefore differently chemically composed, for example. As a result, you may need to collect some extra statistical evidence. Important thing to remember, statistics cannot possibly observe all of the iron in the universe over all time. Without induction, there would be no general conclusions whatsoever and science would perish. In order to support or disprove inductive conclusions, we need to collect enough evidence. Scientists, agronomists, doctors, chemists, etc. need to provide their own research questions and collect data, and then ask statisticians to help and choose statistical paradigm approach to analyze data and make some outcome. In other words, based on statistics, we can make generalized outcome. Two recently mentioned tools meet together in the main questions to be answered. Given observed statistical data, what is the probability that our inductive conclusion hypothesis is true? Such question named Bayesian. There might be few other questions for statisticians to be answered. For example, frequentist question and others. But we don't plan to discuss them now. That was briefly about statistics, which is used by scientists along with probability. Methods of collecting and analyzing data are also heavily used in science to come up with theories and hypotheses. Let's discuss what are parsimony and efficiency in scientific process and how important their role is. From one side, there might be a temptation to collect as much evidence as possible to have more accurate and more complete information in hand to bring your hypothesis. But practice and history shows necessity of trade-off between spending too much time collecting data and preliminary outcome based on parsimony simplicity. And moreover, there is a notable paradigm shift in science towards parsimony rather than better fit to the data. Signal noise. The more you collect data, the more noise appears, and typically this noise is relatively complex, caused by numerous small uncontrolled factors. Noise here in the data is the discrepancy between the true signal and the collected imperfect data. At certain point there would be too much noise from large amount of input data, and there is no need to move forward to collect even more data. It's like extra hissing sound appeared when you're listening your favorite radio. Initial signal comes out without any noise from your radio station's antenna. But with the distance increase from the station's antenna, signal comes to your radio with extra distortion, causing this hissing sound from your speakers. At some point, with large distance, there will be high chance that your signal will be too noisy. So efficiency parsimony tells that we need enough but not extra huge amount of evidence for preparing good statistics, because enough less noisy data will be collected. To follow efficiency, some terms and related techniques used by statisticians. Two of them are population and samples. The set of actual individuals included in an experiment called sample. A wide set of all individuals addressed by researchers' questions and conclusions is population. Again, we're not collecting information about every individual or the whole population. We are making outcome for the whole population based on few individuals within our sample. Is it efficient? Isn't it? It's important to analyze all statistics already collected. Science is expensive, sometimes very expensive. Parsimonious models offer a cost-effective means for gaining accuracy and efficiency. As we mentioned, raw data captures not only all of the signal, but also all of the noise in the raw data. So it's better to stop collecting expensive statistical data at some point and make statistical analysis, which costs far less than data collection. Rule of thumb: a research department should take into consideration all data already collected for analysis. Data worth collecting are also worth analyzing. That was a brief discussion about trade-offs between parsimony, simplicity, efficiency, and huge amount of data to collect for research. This was first part of videos discussing methods and instruments used in science. We started with deductive and inductive logic. Logic in science focused on correct reasoning. Deduction reasons from general to specific, and induction reasons from specific cases to general conclusions. Then we discussed probability and statistics. Probability allows to quantify, estimate a chance for an event to occur or to become real, or for a statement to be true. Statistics is a set of methods used to collect and analyze data. Then we discussed importance of parsimony, efficiency in scientific processes, which tells in short that we need enough but not extra amount of evidence for preparing good statistics. Remember a topic about signal and noise. We mentioned that to help collecting statistics efficiently, terms population and samples are used. We will continue important methods and instruments of science in the second part of the video, Methods of Science. See you there!